Today, we will discuss drinking water purification, which can be found in Chapter 6 of your book titled Basic Environmental Technology by Jerry Nathanson. To do this, we must first discuss potable water or water that is suitable for drinking. You can see here the counts for good water and very poor water, which must be extensively treated before being released for public use. In regards to water quality, in 1974 Congress passed the Safe Drinking Water Act, also known as SDWA. While this is a very extensive act, 2 points are important to note. First, the SDWA applies to public water systems or those that serve 15 connections or 25 people per day for at least 60 days a year. Secondly, the SDWA requires that the public be notified within 24 hours of a violation. As part of the SDWA, drinking water standards have been divided into 2 parts. The first, or primary standards, are those that have to do with public health and are enforced by law. Secondary standards have to do with aesthetics and are not enforced by law. For the primary standards, let's look at 3 divisions: maximum contaminant level, treatment technique, and maximum contaminant level goals. Maximum contaminant levels are the enforceable limits of a contaminant in the water. These are divided into primary and secondary MCLs. Within primary MCL category, we have 5 subdivisions. Primary MCLs assume approximately 2 quarts of water consumption per day for a lifetime. This would give a 1 in a million chance of developing the related health effect. Generally speaking, MCLs that are exceeded do not pose an immediate threat, but instead cause harm over time. In regards to organic chemicals, water supplies must be tested every 3 years. Inorganic chemicals, or those without carbon, must be tested annually. Because microorganisms can cause issues with public health, coliforms must not be found in more than 5% of samples in a month's time. While we often think of turbidity as an aesthetic problem, particles in the water can shield microorganisms from disinfectants. Thus, turbidity must be constantly monitored. Radionuclides are also monitored in public water supplies. Secondary MCLs deal with the aesthetics of water, such as taste, odor, and color. Although there are national standards, states or cities may choose to set more strict secondary MCLs. When a contaminant is difficult or costly to measure, the treatment technique may be dictated as opposed to the MCL. Maximum contaminant level goals, or MCLGs, are just that, goals. However, for known carcinogens, the MCLG is always set to 0. When and how often a municipal source collects water samples is dependent on contaminant and the pollution served. However, unless a sample is to be tested for copper or lead, the line is fully flushed before collecting the sample. Today, we will discuss drinking water purification. Some samples need to be taken every 4 days, of your book, while others only have to be collected every 9 by Jerry Nathanson. Some should be collected in glass containers, while others should be collected in plastic. Some should be cold, while others should remain at ambient temperatures. We must first discuss potable water should be analyzed within a day, while others may be analyzed anytime within 12 months of collection. Good water and very poor water, which must be records should also be kept about each sample for public use. The record should include the name, date, and location to water quality. In 1974, Congress passed the Safe Drinking Water Act, also known as SDWA, and analysis. While this is a very extensive act, should be kept for up to 12 years. First, the SDWA applies to public water systems. The public and the state should be notified. 15 connections or 25 people per day for at least 60 days submitted each month to the appropriate regulatory agency. The SDWA requires Let's now that the public be notified within 24 hours of a violation. We will begin with sedimentation. As part of the SDWA, drinking water standards have been divided into two parts. The first, or primary standards, are those that have to do with public health and are enforced by law. Secondary standards have to do with aesthetics and are not enforced by law. For the primary standards, let's look at three divisions. It is important to know the detention level. To calculate the theoretical time water needs to be in a settling tank to allow sedimentation to occur. Contaminant levels are the enforceable limits of a contaminant in the water. These are divided equal to the volume of water in the secondary MCLs. And Q is the average flow rate. Within primary MCL category, and work we have 5 subdivisions. Primary MCLs assume approximately 2 quarts of water consumption per day for a lifetime. This would give a 1 in a million chance of developing the related health effect. Again, pause your screen to work the problem. MCLs that are exceeded do not pose an immediate threat. Notice in step 4 that we convert from gallons to cubic feet in order to be able to calculate water supplies must be tested every 3 years. We also need to be able to calculate the overflow. The concept of overflow is that suspended particles that settle at a velocity faster than the overflow rate will settle to become sludge in a month's time. While we often think of turbidity as formula to calculate overflow rate, particles in the water can shield microorganisms from disinfectants. Thus, if you are given an overflow rate of 700 gallons per day per cubic are also monitored per square foot, water supplies. Determine the minimum settling velocity of suspended particles needed to remove them from a settling tank. Odor, and color. Notice that particles standards, settle faster than cities may choose to set more strict will become sludge at the bottom of the tank. When a contaminant is difficult or costly to measure, and the overflow treatment technique may be dictated as opposed to the MCL. It is important to note here that the side water depth is the actual level goals, or MCLGs, are just that. 5 feet is also needed. However, for known carcinogens, the MCLG is always you have been presented with, and determine the required diameter of a tank and how often a municipal source collects water samples is dependent on contaminant by the solution on the screen. You should need a diameter of 20 meters. Unless a sample is to be tested for copper or lead, the line additional notes about settling tanks are the terms influent water, effluent water, and sampling procedure is important. Influent water is water that flows to be taken every 4 days, while others only have to be collected every 9 years. Occurs when water some should be collected in glass containers, while others should be collected in plastic. When this occurs, sedimentation may not be able to remain at ambient temperatures. And some samples should be analyzed within a day, while others may be analyzed anytime area is more effective than a tank with a smaller surface area when the volumes are equal. Records should also be kept about each sample. The larger surface area results in a smaller overflow rate, date, and location of the sample. The name of the technician, or a shallow tank with a larger surface area is more desirable than a deep tank with the same volume. And analysis of the sample. These records should be kept for up to 12 years. We will continue our discussion on water quality in our next class. Until then, if a violation is found, the public and the state should be notified. Additionally, results of water testing should be submitted each month to the appropriate regulatory agency. Let's now turn our focus to methods of water purification. We will begin with sedimentation. This is the process by which suspended particles are allowed to settle out. The accumulation at the bottom of the tank is called sludge. The time of this process will vary depending on particle size, density, temperature of the water, and water viscosity. In sedimentation, it is important to know the detention time. To calculate the theoretical time water needs to be in a settling tank to allow sedimentation to occur, we can use the formula here, where T is the detention time, V is equal to the volume of water in the tank, and Q is the average flow rate. Take a minute, pause this video, and work the problem on your screen. If you need to pause the screen again, do so now and check your work. Let's take a look at a different application of this concept. Again, pause your screen to work the problem. You can pause on the next screen to check your answer. Notice in step 4 that we convert from gallons to cubic feet in order to be able to calculate the depth in feet. We also need to be able to calculate the overflow. The concept of overflow is that suspended particles settle at a velocity faster than the overflow rate will We also need to be able to calculate the flow. We also need to be able to calculate the overflow. The concept of overflow is that suspended particles settle at a velocity faster than the overflow. We also need to be able to calculate the overflow. The concept of overflow is that suspended particles that settle at a velocity faster than the overflow rate will settle to become sludge. You can see here the formula to calculate overflow rate. If you are given an overflow rate of 700 gallons per day per square foot, determine the minimum settling velocity of suspended particles needed to remove them from a settling tank. Notice that particles that settle faster than 3.9 feet per hour will become sludge at the bottom of the tank. If you combine the detention time and the overflow rate, you can determine the size of the settling tank needed. It is important to note here that the side water depth is the actual depth of the water. A freeboard of about 1.5 feet is also needed to prevent splashing over the side. Use the formulas you have been presented with and determine the required diameter of a tank for the problem on the screen. Check your work by the solution on the screen. You should need a diameter of 20 meters. A few additional notes about settling tanks are the terms influent water, effluent water, and short-circuiting. Influent water is water that flows into the tank, while effluent water flows out. Short-circuiting occurs when water moves through a tank faster than the detention time. When this occurs, sedimentation may not be able to complete. It is also important to note that a tank with a large surface area is more effective than a tank with a smaller surface area when the volumes are equal. The larger surface area results in a smaller overflow rate. Therefore, a shallow area or a shallow tank with a larger surface area is more desirable than a deep tank with the same volume. We will continue our discussion on water quality in our next class. Until then, please review Chapter 6 of your book. Have a great day.